Hello and welcome to Team 50's presentation for Project 2. Here's some background. As engineers and environmental scientists work towards developing methods of more sustainable energy production, the question of how to store this energy arises. Many solutions of varying efficiencies have been proposed, and one in particular is the focus of this project. There's potential for high efficiency energy storage with the use of a water pumping system that aims to store collected solar energy in the form of gravitational potential energy.
So our main objective for this project was to determine an optimized configuration for the greatest efficiency of the system. We also had to keep in mind cost efficiency. However, our group primarily focused on the overall efficiency of the system. With that being said, we needed to create a model that would output efficiency for certain inputs that the user could choose, while we held other variables constant that we had determined as a group. We also needed to research several things for this project, including cultural factors such as ancient burial sites, because our location that we ended up choosing was a Native American burial ground. And we also needed to research physical factors such as leakage to determine if we needed to include that in our model. And lastly, we needed to research similar systems to determine the optimal site and other features that we ultimately needed to make decisions on, such as pumps, pipes, turbines, and vents. So the first decision that we wanted to make was determining a site, and we began by making pros and cons of each site along with a decision matrix that we created, and the decision matrix prioritized elevation of the reservoir in order to get a good initial potential energy for the system and the site prep cost as well. After doing some research, we aimed for a cheap system with at least 75% efficiency, and we decided a pipe width of 1.25 meters because using a smaller width ultimately made the cost go down a lot, and it did not sacrifice much in terms of efficiency. And we decided on a reservoir depth of 20 meters. So we used our software model to find the cheapest combination with our goal efficiency in mind.
This code model basically utilized the universal accounting equation and plugged in various equations that were given to us by the technical team in the project documents. Essentially, we had an energy amount going into the system, which we calculated using the model. And then we noticed that the system created 0 megawatts, but it did consume a lot of energy due to pipe friction, both up and down, bends in the pipes, and pump loss and turbine loss.
There are a lot of other factors that determined our site and our cost choices. Site 2 is a location of a Native American burial ground, and we budgeted an extra $8,000 to investigate whether we would have to move burials or not. Pending this investigation, more money may need to be invested in the project to remove and relocate some burials. We also considered whether to factor in pipe leakage, and we eventually concluded that leaks would not be a significant problem. This is because we used the equation flow rate equals the velocity of the water times the area, and we used a pretty significant hole of 4 centimeters, and if the water is moving at 20 meters per second out of the hole, which is also a very high rate. And if it was doing this for a whole day, only 0.42% of our water would be lost, and this would not, in the grand scheme of things, be a major issue in our model. And then to combat reservoir leaking, we budgeted to have the concrete wall sealed, adding an additional $144,000 to the total cost of construction. This makes it so we don't have to worry about water seeping into the ground or other things getting into the water. So for our model, we started off with some basic inputs that we wanted to be able to change when deciding the efficiency of our model. These things included the pump efficiency, the pump flow rate, the pipe diameter, the pipe friction, the fit factor for a bend, the turbine efficiency, and the turbine flow rate. Originally, we did have some of these things hard-coded into our model, such as the pipe length and the reservoir elevation and depth based on our site, but we ended up making them into inputs as we did mess around with those values just a little bit. And then for our computations, we started off with some basic computations such as the pipe area, which is just the area of a circle. And then we calculated the velocity of the water going up and down the pipes, which is dependent upon the pump flow rate and the pipe area and the turbine flow rate. Then we started calculating energy lost due to certain things such as the turbine loss. And then we used a universal counting equation to find the amount of mass that we would need in the reservoir based on our inputs. And this was based off of the universal counting equation where it's final minus initial equals input minus output plus generated minus consumed. And the input is mgh plus the reservoir depth divided by 2. And then the output is the energy output, so E out. And then all of the things, all of the energy consumed when the water is flowing down. We then calculated the pipe friction of the water going up and down, and then the bend loss going up and down, and we only had one bend, so we didn't need 2 bends there. And then we used, to calculate EN, we used a different accounting equation, which was the final and initial values were 0. And then we had E in and E out and all of the combined losses in the system. So we had this equation here where it's the output plus all of these consumed values divided by the pump efficiency, which was determined by the pump loss equation, which equals 1 minus the pump efficiency times E in. And then we converted these values into megawatt hours as they were in joules before. And then we found the reservoir area that we would need based on the amount of mass we had and our reservoir depth, which we chose to be 20 meters.
After playing around with different inputs into the code, we created a set of variables that we believe optimize the efficiency of our solar energy storage system. First off, we selected a premium pump with 92% efficiency. We created a pump flow of 20 cubic meters per second, a pipe diameter of 1.25 meters for a length of 187.74 meters. Our pipe friction we chose was Glorious, which had a Darcy friction factor of 0.002. The reservoir depth we chose was 20 meters at an elevation of 100 meters. Our pipe loss coefficient for the one bend that we had was 0.22, and we used a turbine selection of Mondo with 94% efficiency and a flow of 11 cubic meters per second. As we mentioned before, we played around with the variables quite a bit, but we believe that this set of variables created the optimal efficiency and cost correlation. When the code is run, it asks you to input a bunch of the variables, and once it's done, it'll output a bunch of different variables such as the efficiency, which is what we were really testing for. So as you can see, once the code is done running, it outputs the pipe area, velocities, and effective elevation, which are all intermediate variables, as well as the mass that should be stored in the reservoir, and then the more crucial variables, which are the area of the reservoir, the energy that should be inputted into the system, the efficiency of the system, and the time to fill and empty. So the energy in that we require is 150.54 megawatt hours, which creates an efficiency of our system of 0.8 or 80%. And the time to fill is 6 hours, which we believed would be a good time because if the system only gets one sunny day every once in a while, we want it to be able to fill up pretty quickly. And the time to empty is 10.97 hours. We chose this because this was based off of the flow rate that we chose, and we chose this because we wanted the energy to be usable within the 12 hours, but we also didn't want the, if the water was flowing at a faster rate, it decreased the efficiency. So we wanted to make it at the perfect medium.
So in conclusion, we wanted to create as efficient a model as possible while keeping it under an umbrella cost of $800,000. We actually exceeded our target efficiency of 75% with a total of 80% efficiency at the end of our calculations. Our model of code allowed us to optimize our system by placing different variable inputs into that code, essentially a trial and error process. It took a lot of time, but we ended up with a set of variables that we are confident produces a very efficient system. Thank you for watching our presentation on Project 2. We hope to see you next time.